Hello and welcome to Lecture 1 in the perhaps somewhat intimidatingly named unit, The Principle of Relativity in Phys 1104. In this lecture we're going to be meeting one of the key ideas we need for going forward in the course, the idea of an inertial reference frame. One of the starting points for this lecture is something that we saw during Unit 5, which was relative velocity. So here's just a reminder of how we calculate a relative velocity and the picture we use to argue about it. And if this doesn't look familiar to you, then you should really go back and look at the part in Unit 5 where I'm talking about relative velocity. Let's start with that idea of relative velocity and what's hopefully a fairly familiar and intuitive situation, and build on your intuition to see how motion is relative. When we talk about motion, we have to pay attention to what it is relative to, or what it's being measured relative to. So here's an observer, a person who I've named E because they are in the Earth reference frame. There's a new word. A reference frame is a set of axes and a clock, or in other words, it's a point of view from which measurements could be made. Well, just as observer E can make measurements, observer M, who's moving along in this car, and so I'm calling them reference frame M, moving with respect to the Earth, they can also make measurements. So E has a set of axes that they use in making their measurements. M also has a set of axes that they use, but their axes, remember, moves along with them and the car. And notice all the double subscripts here because these are relative velocities. And I'll just point out about this formula that, while I don't want you to memorize any formulas, this one's really simple. The only difficult thing is remembering which thing gets subtracted from which. And you can see it here. Why is Vm2 pointing back to the left? Probably intuitively you see that it should, but you can understand that as being that we are taking V2, which is 0, and subtracting Vm from it, and so we get something off to the left. And notice that I could have called these two velocities VE1 and VEM, but you probably feel there are quite enough subscripts in this course already, and so when I'm talking about velocities relative to the Earth frame, because that's the frame we most often make measurements from, it's sort of our default, I'll tend to drop the E's. This whole unit is really formed around a single central question. And it'll take us the whole unit to answer it, but I might as well get the question itself out of the way right now. Let's think about this person and their set of axes, which they're using to make measurements on a cart collision. And this is a 2-to-1 inertia ratio. And so this person sees, look, the delta V of the one cart is half the size of the other, and so they conclude that the ratio of inertias is equal to the negative of the inverse ratio of the delta V's. And so from this person would conclude that this system's momentum is conserved. This person can also see from their measurements that the relative speed of the carts before the collision is the same as the relative speed after, and so they would also conclude that this is an elastic collision. Well, the central question of this unit is, remember Trogdor and Spiff, who are moving relative to this person, do Trogdor and Spiff agree? Remember that they are moving relative to these carts, and so that will affect their velocity measurements. So do these equations still work out for them despite their motion so that they agree with this person that the system's momentum and energy are being conserved? Or to put it another way, does the behavior of a system change if we view it while we are in motion? We need to know about moving axes. So let's think about that. Here's a cart E that's stationary relative to the Earth, and a cart M that's moving relative to the Earth. And we have a ruler E, and that ruler E is called E because it's fixed to the track, or it's stationary relative to the Earth. And note, it really is an axis, right? What is an axis? Your x-axis is a ruler that you've stuck in some direction, and then your y-axis is just another ruler that you've stuck perpendicular to it. So moving axes are moving rulers. Well, so let's have a moving ruler. Here's a ruler M, which is attached to cart M and moving along with it. And so that's just another axis, but this one is moving. And we can now measure the positions of these carts relative to both rulers. Have a look at the measurements I've made and verify these graphs. And of course, we can see in the graphs that cart E isn't moving relative to ruler E, and cart M isn't moving to ruler M, so those x components of velocity are both 0. And then we can pull the other velocities off of the graphs. And you see, as we would expect, the x component of one of these velocities is just the negative of the other, as we would expect from our relative motion equation. Rulers E and M are both sort of special cases because each one is stationary relative to one of the carts. So here's another ruler, C. It's C because I'm so creative, and it's moving relative to Earth at 0.3 centimeters per second to the right. And again, we can just measure the positions relative to it, and we're going to get an x versus t graph like this. And now relative to that ruler, both of the carts are moving. And again, we can get the velocities off. And you should now look at the various velocity components I've calculated out of these graphs and just verify that this is all obeying this equation here for relative velocity. There's another useful equation that sometimes comes up that we'll use later. For some object O, just any object relative to rulers A and B, we have this equation. And so what we have here is the velocity of O relative to some ruler A, and the velocity of some ruler B relative to ruler A, and then the velocity of O relative to ruler B. So you can pull all those velocities out of the examples I've just gone through and verify again that this equation holds. We see that depending on which ruler we use, we get different answers for the velocities. But what's really important here isn't that the velocities differ depending on which ruler we use. What's important is what doesn't change. Notice that all the x versus t graphs we've been looking at are straight lines. So these carts are all moving with constant velocity, but more importantly, we see no matter which of these rulers we use that they're moving with constant velocity. So we can conclude that an object moving at constant velocity in the Earth reference frame will also move at a constant velocity in any frame that's moving at a constant velocity relative to the Earth. Notice what this means, because these carts presumably have constant inertias as well as constant velocities, so these carts are isolated. That means that no matter which of these rulers we use, we agree that the carts are isolated. Does that mean we might have actually answered part of the central question of this unit? We can go a little further because the relative speed of the carts is also the same no matter which ruler we use. Check! It's 0.8 centimeters per second for all three rulers I used. Wasn't relative speed kind of important? Maybe we've just answered another part of the central question. Here's you and Sam, right? We haven't met Sam in a few lectures, but we know you and Sam rarely agree on things, and we certainly can see that if we're putting you and Sam in different reference frames, you're going to disagree about velocities of things, so nothing new there. But what we're going to see is that there's some surprising agreement here. So here's you in your frame, and I've put you in the Earth frame. And so cart M is moving at a constant velocity relative to the Earth. As we've seen, you might as well think of this as carts E and M from that previous example, except now you and Sam are standing on them. So you say Sam and cart M are moving at constant velocity, and because their inertia is also constant as well as their velocity, you would also say that they have a constant momentum, which means, as far as you're concerned, Sam and cart M are an isolated system. Well, by the same argument, according to Sam, you and cart E are moving at a constant velocity. And so you have a constant momentum, and so according to Sam, you and cart E are an isolated system. But you also agree, each of you believes that you are moving at a constant velocity. You believe you're moving at a constant velocity. It happens to be 0. Sam believes that Sam is moving at a constant velocity, also 0. And so each of you believe that you are in an isolated system. So look, Sam believes you are in an isolated system. You believe you are in an isolated system. You believe Sam is in an isolated system, and so does Sam. Well, let's bring ruler C back in. So Trogdor the Burninator is riding along on ruler C. And relative to ruler C, both you and Sam are moving, but again, both at constant velocity. And so Trogdor, again by exactly the same set of arguments, agrees that you are in an isolated system and Sam is also in an isolated system. So what we've just seen is that all observers in reference frames moving with constant velocity relative to the Earth agree on whether systems are isolated. Or to put it another way, they agree that isolated objects move at constant velocity or resist velocity changes. We would say that they agree about the principle that things have inertia. And so since everyone in reference frames like this agree about the principle that things have inertia, we call these inertial reference frames. Any frame moving at a constant velocity relative to the Earth is an inertial reference frame. Now, I'm going to pull out this law from a few lectures back, and we're going to improve it. We said that objects in motion move at constant velocity unless their velocity is changed by interactions. Well, we can improve that because anything that is interacting with its environment is not isolated. And so we can reword this in a much briefer form by simply saying that any isolated object moves at constant velocity. And I'll point out that moving at constant velocity includes being at rest, right? That's just a special case of moving at constant velocity. But we can improve this further. We can make it more powerful because of what we just found out about different observers in inertial frames. We can say that as viewed from any inertial reference frame, any isolated object moves at constant velocity. And I will now not have to mess with this law anymore. This is as general and as absolute a law as we know of in physics. What if we have a reference frame that isn't inertial, a non-inertial reference frame, or in other words, a frame that is accelerating relative to the Earth? So here's an example. Here you are in the Earth frame, and Sam is now on cart A, which is accelerating because it's being pushed on by a great big spring. So from your perspective, this cart B, which is just a low-friction cart sitting stationary on a surface, is isolated. It's not interacting. It's a low-friction cart. And unsurprisingly, it has constant, in this case 0, momentum. Unsurprising, this is the law of inertia at work. You can also look at Sam. And to you, Sam is and the cart A are clearly interacting with the environment because of that great big spring that's crossing from the environment into the system, across the system boundary. And also you can see that they're accelerating, so clearly their momentum is changing. So all of this is as we expect. But now let's see what things are like from Sam's point of view. In Sam's accelerating reference frame, or non-inertial reference frame, Sam can see just as well as you can that cart B isn't interacting with the environment. It's a low-friction cart sitting on a surface. So it's isolated. But according to Sam, its momentum is changing because it appears to be accelerating towards Sam. Also, Sam can also see as well as you that cart A is interacting with the environment. There's that great big spring pushing on it. But as far as Sam is concerned, Sam being stubborn as usual, cart A is remaining at rest relative to Sam. And so both of these are violations of the law of inertia. The main point here is that the law of inertia doesn't apply in a non-inertial reference frame. And this makes non-inertial reference frames often inconvenient. You should avoid defining axes in a non-inertial reference frame.